All right, so today we're going to talk about data modeling and design. So, on this session, we'll be learning how to build structure behind your information systems. So, why does structure matter? First, we need to recognize that data is a core asset. So, every modern information system depends on data to function, to communicate, and make decisions. So, every form of digital interaction has a way of either storing data, pulling data, or updating data that is being stored in a warehouse or in a data lake. And without structure, chaos follows. So unorganized data is difficult to query, maintain, or trust, which leads to errors and inefficiencies. And that's where modeling fixes that issue for us, because data modeling and design pretty much gives us the information, a clear logical structure that systems can rely on. So why does data modeling matter? One, it helps reduce duplication. This helps in eliminating redundant data stored across multiple locations. A good example of this is if you have two different tables that have certain information on there that pretty much says the same thing. It wouldn't make sense to connect those two, send those two tables to the whole database and pull information that is pretty much duplicated on both sides. So this is where like data modeling comes in, where we can fix things like relationships and pretty much pull certain data from certain tables that we want to be accessed by the system that we're building. It also helps in improving accuracy. So in the case of duplication, for example, if I were to get a total number of, let's say, student, or in fact, let's just say sales, right? And I had some duplications in my whole database, that could bring back wrong data, because those duplications would be considered in the data that has been returned to the person querying the system. Whereas if we focused on improving that with data modeling, all of that duplication would be dealt with, all of that duplication would be sorted out, which would help us arrive at the accurate figure of whatever we're querying. And then it also helps us understand the model better. So clear models help developers and stakeholders see how data connects. And another one is it supports better decisions, just like the example that I gave. If we are sure that we're getting accurate data from the system that we're querying, we can make better decisions based off of that data. However, if we weren't getting accurate data, the decisions that we'll be making will be skewed. Therefore, it wouldn't actually be the reality of the outcome of the system. It could be for a business, could be for an organization that is, dealing with student data, or, different industries, pretty much. Then it also helps in enhancing scalability. A solid model allows systems to grow without breaking down. So what is the major difference between modeling and design? So data modeling during this phase is pretty much just planning how the data is exists, where it exists, and how it is structured, and the entities that have to relate with one another within that data. While data design is where you actually build what you've planned. So this is where you start creating tables, start creating schemas and storage structures. This is pretty much where you implement the whole modeling that you've done. So what are the core components of a data model? The first one I'll touch on is entities. So entities are basically like an object, right? An object has different features or attributes to it. A good example of that is a human being. A human being, for example, is an object. And a human being has eyes, has ears, has nose. So the nose, the eyes, the ears, the hands, the mouth, those are the attributes of that object. So if I were to give a proper data related example, that would be, for example, a course table. A course table has different details, like the course name, the course level, or the course level if it's maybe an undergraduate course or a master's course, for example, the course code. So those course name, course code, those are the attributes, whereas the course table itself is the entity, and which obviously will lead us to the next point, which is the attributes that I spoke about. And this pretty much just defines the entity that we've identified, which is, for a person, we could say is the name of the person, the ID of that person, the email, and so on and so forth. Then the next is the relationships. The relationships is pretty much how the different entities connect with one another. In the should I say, with the university standpoint or example, we can have like a student enrolling into a course. Now we have the student entity and we have the course entity, and we then have to look at how those entities could relate to each other, right? Can that student be enrolled to that course multiple times, or can that student only be enrolled to that course one time, which obviously would then bring about, if it's a one-to-one relationship, if it's a one-to-many relationship, many-to-one relation, and all of that, and many-to-many, and all of that stuff. And then the constraints. The constraint is pretty much the rules that govern the data integrity. So an example of that is pretty much a student ID not being null and has to be unique, as you do not want a student table that has multiple duplicates of student ID. Because if we say this is a student ID for me and this is a student ID for yourselves, for example, you wouldn't want my student ID to be the same with your student ID. So again, that could bring about issues later on when we're querying that data. So this is where we add all of those constraints to ensure accuracy and reliability for the data that we are keeping. So what are the levels of data modeling? The first level I'll say is the physical model, which is the tables, the data types, the indexings for implementation. So this is where we define the tables that we'll need for the whole database for whatever system we're building. The data types, for example, the ID can be a numeric value. The student name can be a char. We can have date of birth can be date value and all of that stuff. Then the next one will be the logical model. So the logical model is where we talk about the entities, the attributes, the relationships, defining them. This is where we then go a step further away from just defining the actual tables and the data types to then recognizing the different tables that we have, the attributes and how to connect to each other. And then the conceptual model is pretty much high level business, where we then start querying the data in terms of like getting useful information from the data. So each level pretty much adds greater technical detail from a broad business view down to the precise structure implemented in a real database system. So what are data modeling techniques? Data modeling techniques are pretty much, shall I say, ways we can get to model data to obviously fit into the requirements of our system. The first one is the entity relationship model, which is ER. And the best, I don't know if you guys have heard of this, but there's something called ER diagram, which is pretty much entity relationship diagram that you can build on like tools like Draw.io. I think there's another one, I forgot, Lucid Charts. Yeah, so on there, we can build entity relationship models, and these are basically visual diagrams showing us entities and their relationships. This is most widely used technique across the board. Like a lot of people like that visual diagram of seeing a box containing the entity with the attributes. So it could be the name, the ID, and all of that stuff, and different other entities, and pretty much align connecting those entities to define like the relationship between one entity and the other. The second is relational model. Relational model pretty much organizes data into tables. That's relations with rows and columns. This forms the basis of SQL databases. So in this sense, we're storing all of that information into different tables, rows and columns that we can then query within our SQL database. And obviously, if you know SQL, that's structured query language. And then there's the hierarchical model. This structures data as a tree with parent-child relationships used in early mainframe systems. So in this form of model, we're pretty much arranging or like structuring the whole database in a hierarchical model. So for example, we could say the bigger parent is I'll give a real life example. The bigger parent is let's say a person, right? That's a bigger entity. Now, if you look into that, a person has hands, a person has eyes, a person has ears. Then those are the smaller entities, right? And within those, we can then check how many eyes does a person have, how many ears does a person have, how many hands does a person have, and within the hands, for example, we can also check how many fingers does a person have within those hands. So like that's pretty much like the hierarchical model. So it's kind of like a child element, but within that over that child element there is a parent element that kind of like oversees all of that data. And then there's the network model, which extends the hierarchical model to allow many-to-many relationships between records. So this is where you have like different data records being connected in a network type of, should I say, model, where you can have multiple information being pulled or being compared with one another between different entities. Then we've got the keys and normalization. So keys will basically talk about two major types, which is primary key and foreign key. So the primary key is a unique identifier for each record in a table. So no two rows share the same value. The example that I gave earlier about student ID is a good example of primary key. We can't have two different people with the same student ID. That will bring about issues, because then when you're trying to query the data of, oh, give me the name of this student with the student ID, it now has two rows. Now it doesn't know which of that actual student you want their name. Do you get what I mean? So that is where we have to like add constraints in terms of like making sure the primary key is always has a value, is not null, and it's not duplicated. Then we've got the foreign key. The foreign key is basically a field that links one table to another, creating a relationship between records. So this is where we then have to think about creating relationships between a record between two or multiple different records. A good example of that is a product and a sales table. So a product table would have a primary ID of product ID, while a sales table would have a sales ID, but would also have a foreign key of a product ID, because within that sales table, we want to know which product did we sell. Because a good example is I can sell a certain product, right? But that would be a different sales ID. For example, if I, as a person, go on Amazon and I buy, let's say, a bottle of water for I buy that twice. Now, those are two different sales ID. However, they will have the same product ID if I actually chose to buy that same product. So this is where like the primary key and foreign key comes in, to kind of like know, if I'm looking into the sales data, how can I pinpoint what product that is from having the product ID? That's how like foreign key and primary key comes in to help us with the relationship between different entities. And then there's normalization. Normalization is basically a process of organizing tables to reduce redundancy and improve consistency, which is applied in different stages. So there's the 1NF, 2NF, 3NF, and it even goes up to 4NF. And basically this is pretty much just the steps of things that you will applications. A good one is obviously checking for duplicated records within a specific entity. And another one is also, if you're connecting or you're building the relationship between different entities, you want to make sure that you're not pulling the same data that could also be pulled from another entity that you've connected to as well. So it's more of like three tables can connect to each other or can talk to each other without necessarily having a there is customer table, product table, and sales table. Now, I don't need to connect the product table and the customer together and connect the product again to the sales and then connect the sales to the customer. That is just a web-like connection. All I need to do is pretty much connect the customer to the sales table, connect the sales table to the product table. And with that single linear kind of connection, I can get details from the sales table, or when I query the sales customer table, I can get details of the types of products they've been purchasing because of that line of connection. So this is where like normalization helps us get rid of those unnecessary redundancies. So what are the benefits and challenges? Some of the benefits with data modeling and design is pretty much data integrity. Rules and constraints help keep data accurate and consistent. There's also easy maintenance. So well-structured models are easier to update and extend, because if it's properly structured, if it's properly designed, we know there are no duplications. If we want to scale or if we want to maintain, we can easily maintain what is already working and what is already accurate. However, if there are issues in our model and design that we've not considered, and now the business is now scaled to a certain point, but then is now bringing issues in terms of scaling bigger, then we then have to look at, oh, how do we fix this previous backlog of redundancies, of duplications that we didn't address initially? Another one is efficient querying. So good design speeds up data retrieval and reporting, which is kind of like the example I gave in terms of the person to sales to product table. That in itself helps us query the should I say database correctly and properly, instead of having a different web of like connections between each entity, which could cause issues when we're trying to query the database. And then scalability, just like I mentioned earlier, systems built on solid models, they adapt to future growth. So because of the easy and clean, and because of the clean flow and design of the data that has been built, it allows for easy scalability. And then the challenges, though, is you have to understand the requirements. So you kind of need to know about the business, so you're not misinterpreting the business needs, which leads to poor model decisions. So in the terms of trying to design a data or model a data for a business, you need to pretty much understand what the business is about, what they're trying to gain from this data modeling system or information that they're trying to build. Because if you don't understand that and you build something that isn't really in line with the business needs, is pretty much going to crumble and going to bring challenges later. Because then whatever you gather in terms of the business's goals, the business's should I say architecture, is what you're going to use to build or design the data or the data model. So another one is also managing complexity. So large systems with many entities can become difficult to model clearly. And this is a university is a very good example of this, because a university has different departments within them, and trying to manage or design, or should I say model a data or create a data model for a university like that can be very difficult, because then you're looking at different entities that have different values, but would also have certain duplicated values in so many different ways. And you're thinking, how can I connect this entity, or how does this entity connect with this entity, without necessarily, obviously, again, going back to the initial thing, without necessarily creating a web of just connections, and instead creating a proper linear connection between the different entities to allow for proper querying. And then we also think of designing for growth. Anticipating future data needs requires careful foresight. And this is where you have to think of, okay, if we're designing this now, but we also need to, we also have to think of if the business grows, what are the extra things that we might want to add on to the business, which obviously would mean we have to update or make certain changes to the data model. Would what we're building now allow us for that? So when you start considering all of this, it starts making the whole process of like data modeling become slightly more complex, which is pretty much the challenges I'd say you will find in data modeling and design. So the conclusion is pretty much data modeling helps us define structure. It maps out entities, attributes, and relationships before any system is built. The second is data design enables implementation. It turns that plan into a functioning, queryable database or system. And the third is pretty much good design improves reliability. Systems built on sound data models are more consistent, maintainable, and scalable. So well-structured data is the foundation of every successful system. That will be pretty much it. So that is the end of the whole presentation about data modeling and data design. And if you have any questions, let me hear it. I'm just gonna wait for a couple seconds to see if we've got any questions.